Hello and welcome to RedisConf 2021. My name is Prasanjit and today I'll tell you a story. This story is a DevOps engineer's account of challenges, solutions, and learnings when we work on a high traffic software stack and that handles millions of requests every second. I'll speak about these challenges faced as our product grew from 10,000 users to 100,000 users and eventually up to 2 million subscribers, and our learnings and essentially how Redis had a part to play with augmenting the site reliability. We will focus more on the systems designs part, the infrastructural challenges, and less on the things from an application developer's point of view. So before we go on with our story, let me quickly introduce myself. Well, my name is Prasanjit and I'm the Director of Cloud and DevOps practice at STARZPLAY Dubai. Along with platform engineering, I am passionate about learning and teaching, and I have trained over 20,000 students at Coursera and EdTech platforms. And with my team at STARZPLAY, I am responsible for deployments and site reliability. And at STARZPLAY, we are a video on demand service that streams movies, TV series, documentaries, kids entertainment, and live sports to 20 plus countries across the Middle East and North Africa. And we also support OTT platforms in Southeast Asia. We have a live subscriber base close to 2 million, and our apps are installed over more than 10 million devices. And so that brings a lot of requests, more than 30,000 requests ready to bombard the platform every minute round the clock, and that's a huge number. Well, with these requests come the challenges, and now to keep the show running, we come up with solutions and solutions to these challenges, of course, and we learn a lot from these challenges and while implementing these solutions. So I'll talk about all that. So this is how it begins. Once upon a time, not so long ago, we started up our OTT platform, and we had undergone infrastructure modernization. So from the rusty monolith software stack, we had shiny new microservices with CI/CD pipelines, multi-AZ databases. We had automated deployments, container orchestrators, NoSQL databases, and the list goes on. We were also working on a well-defined release management process. We were working on monitoring dashboards, and we were adding logging, tracing, and all this was supported by DevOps practices. And we were working on teams that would continuously monitor and ensure site reliability. Wow, that sounds like a fairy tale. Well, we'll come to that in a while. From a high level, this is how the stack looked like at that point. A hybrid of monolith and microservices. The monolith still there because that's where we started out and eventually moved on to microservices. So there's that phase when you're running both in parallel. So you have your microservices new stack going as well as the monolith still existing alongside. And that was when our service was getting noticed and customer base was growing as well. And with this, we had growth in number, we had growth in traffic. And that is when we saw our first challenge. Well, what was that? High response time. In simple words, a slow application, which meant a not so good user experience. It meant timeouts, retries, errors resulting out of this slowness, and we were digging into the reason. Why was that? So let's understand the situation. To do that, let's revisit the stack. If you look at this diagram, you see a simple three-tier architecture with a presentation layer, with a web portal, mobile and TV apps, and application layer of microservices with a designated function, and finally a database layer, the single source of truth for our system. The problem here is when you have traffic in high numbers, then the database would get overwhelmed with requests, exceed connection limits, breach disk I/O, and would eventually lead to slowness or outage. The solution is a cliche, using a cache. And what we did just that. We put up a Redis cache over there, and so our application now would look something like this. The application would check a cache for data and would retrieve it from the cache if it's present there, or else fetch it from the database and update the cache. This reduced unnecessary network overhead and stress on the DB. Now, cache memory temporarily stores the most frequent used data, and it's a great way to get that data that is used most often because the retrieval process is super fast. However, cache memory is limited in size, and there needs to be a way to manage what data needs to be removed and from the cache so that we would have space for new data to come in. That's where LRU Cache comes in. It's a cache replacement algorithm that removes the least recently used data to make room for new data. So we did this and some other tweaks on the server side, and finally we're able to resolve the problem. So focusing on caching and Redis, let's stick to this theme and not diverge into what we did, like what are the tweaks we did on the server side. Now that we had figured out the slowness and its solution, another problem was waiting for us. Out of memory. Now, what was this problem? We know that Redis is an in-memory cache. Now, that's the reason it's fast. So what happens when Redis runs out of memory? So that's the problem we faced here. When dealing with this problem, we came across a curious case of expiring keys. All the keys in Redis are set with an expire. So we assume that when the keys are expired, the keys and the values would be automatically removed by Redis immediately, and the memory would be reclaimed. We thought that would be just natural, that's the thing that's expected, but we were wrong. The fact that Redis does not remove all the expired keys immediately was something we learned in due course. In fact, Redis has two mechanisms for removing the expired keys. One, the expired key will be removed when the client tries to access it. Two, periodically Redis tests a few keys at random expire set, and all the keys that are already expired are deleted from the key space. So having discovered that, what we did is simply ran a scan command across all the keys and successfully reduced Redis memory usage by deleting expired keys and freeing up the memory for new keys to come up. Well, that was something new for us. Further, in the Redis configuration, we set up max memory. That was the maximum memory that will be used by Redis. Then what happens is that when we hit the memory limit, Redis provides some eviction policy that can be used when that limit is reached. So Redis has inherently many such policies, but by default, max memory is set at unlimited, and max memory policy is set at no eviction. So if someone doesn't know that and just deploys Redis vanilla, then what happens, you come with these default settings, and that would lead to errors if the max memory limit is reached. So we learned it the hard way, and what we did is we set a finite max memory depending upon our volume of key value pairs, and the max memory policy was set to volatile TTL. I'm telling this so that others who are on similar situations can practice this and resolve their issues. Well, problem number 2 was done and dusted. The curious case about expiring keys, and how to set the max memory in Redis so that you get free memory for new coming keys. Alright, so by then we had moved to 500k subscribers and we had new problems to solve. So this problem is the problem of a cache failure. Now, let me explain. You're using Redis and your server goes down for some reason, or your disk fails. Even if the server is running, your disk fails, and you have no high availability mechanism in place, or you're a small startup, you cannot afford HA yet. So that leads to requests hammering your backend, your databases again. So how do you deal with that? Well, we are DevOps, so we have solutions to everything. We have images of Redis servers ready, stored up in the cloud, so we can just spin up new servers in minutes. But it isn't that easy. That doesn't solve the problem actually. Why? Because new servers that spin up are clean slates. Like, their hard disks would not have the latest cache data. They would have the snapshots of images that when you made them. So it would take minutes or sometimes hours for cache warming. So how did we solve this? Well, Redis had an answer: AOF Snapshots. Now, what is that? Redis database persistence performs point-in-time snapshots of your dataset at specified intervals. Now, AOF, that stands for append-only file, the AOF persistent logs write every operation received by the server that will be played again at server startup, and reconstructing the original dataset, it'll recreate everything that was logged in and recreate the original dataset from those snapshot logs. So even when we spin up new instances, we can restore the cache data. Another problem done understood. So it was that simple. Just have your AOF snapshots in there, and server goes down, spin up a new server, takes a couple of minutes, and then restore your AOF snapshots and solve the problem. But hang on, a bigger one is waiting for us. That's the thundering herds. Now, what is a thundering herd problem? See, when millions of people tune in to thousands of video requests, we see a cache miss at the edge cache servers. So when does it happen? When millions of people tune in to a live broadcast simultaneously, there would be a sudden spike. So when there is a spike and you do not have something in your edge cache, then potentially hundreds of thousands of these video requests will see a cache miss at the edge cache, and those queries suddenly will herd along and hit the origin, and these live processing origin servers are not designed to handle such concurrent loads. So what happens in that case is that they crash. So how do we deal with that is we solve this thundering herd problem by creating request queues at the edge cache servers, allowing one request to go through to the live stream server and return the content to the edge cache, where it is distributed to the rest of the queue all at once. How does that work? Let me explain. Well, the solution is something called cache promises. Okay, promise is an object that represents a unit of work producing a result that will be fulfilled at some point in future. You can wait on this promise to be complete, and when it is, you can fetch the resulting value. When there are n concurrent requests that do an atomic check whether the key exists in the cache, then we use Redis transaction to do this. Atomically set a special value that signals the nodes and the key is reserved, thus a leader from the end request can be appointed. Now this leader node can then do async requests to the backend. In simple words, let me explain this. Like, what happens here is there's a leader node that accumulates n number of requests, doesn't send it back to the origin server, and when all these requests that desire the same result are accumulated, it asynchronously sends one common request to the backend instead of n number of requests. So that way, the herds of requests thundering into the backend are tackled. So it is accumulated and asynchronously sent back to the backend. So the backend gets some space to breathe. So that is how we still keep running our shows. Well, What was next? Oops, server is down. At this point, we were nearing 1 million subscribers and still not on HA. Just the data persistence and the recovery mechanism that I discussed earlier from the AOF snapshots, that was there, but no HA yet. So what happens when server goes down? It results in a brief outage, right? So now the time taken to restore the servers back is the recovery time. In DevOps terms, we have something that we call error budget. Now, error budget is the amount of time we can afford being down or see errors before it becomes apparent. Now, with the growing subscriber base and the traffic, the error budget narrows because people start noticing and start making a noise about the inconsistencies on of the platform on different social platforms, say Twitter or Facebook. So at this point, we needed HA. So what did we do? We built HA Redis master slave cluster, split read writes, and the nodes used a gossip protocol to propagate information about the cluster in order to discover new nodes, to send ping packets to make sure all the nodes are working properly, and to send cluster messages needed to signal specific conditions. So that is how we created a cluster that syncs itself and stays together with n number of nodes. And we, of course, got to high availability. We were able to split read writes and so on. And this worked well for us until we saw even more traffic during our promotions or when we added new live sport add-ons to our platform. And as we approached 2 million subscribers, we started seeing capacity issues again due to high traffic. So how did we solve that again? Well, high traffic problems are difficult to solve actually, because you know everything is right, but you need to have the capability for your stack to be elastic. In this case, we needed our Redis stack to auto scale on demand or whenever the load is high. So how does auto scaling work with Redis? Well, one way to make autoscaling work with Redis is to use a horizontal pod autoscaler. That, of course, will work if your Redis cluster is on Kubernetes. And that automatically scales the number of pods in a replication controller, a deployment replica set or a stateful set based on the CPU utilization. You can also use controllers like Mastro or Keda that can achieve this. So your cluster grows based on the traffic or CPU usage, and new nodes are added, and it shrinks back when the load subside. So this is how we did it. Well, so that is where we stand at this moment. So can we say that the story ends and we lived happily ever after? I don't think so. Why? All I can say is like we hit a wall at every step, learned something there, moved on to the next step, and we grew. We kept growing and we continue growing, and we are looking forward to what is coming. Probably next would be active geo-replication cluster. We could have multi-cloud replication, multi-tenant, infinite scaling, and all those good features that Redis Enterprise has to offer. So we'll keep trying from our failures and get to success, rinse and repeat. All right, so what is the moral of the story? One, failures are normal. It's good to have issues, and it's good to fail fast so that solutions are applied quickly before the problem magnifies. Two, continuous improvement is one of the key tenets of DevOps, and it is a key to sustain enterprise architectures. Three, caching done right helps site reliability teams stay within error budgets. And four, of course, if your cache is Redis, it has so many features that you can fine-tune it to augment site reliability. So what was the biggest takeaway? The cost of failure is education. Let me elaborate quickly. The great opportunity that exists when we see failures is learning. So our experience with Redis taught us just that, and from a DevOps perspective, we found Redis aligned with our goals of achieving a highly available and resilient and a highly responsive software stack. Well, that is all from me today. If you have questions, feel free to ask me in the follow-up session or over email. Hope you enjoyed our story, and stay tuned to other sessions today at RedisConf 2021. Thank you.